Up until now, we've only really tested designs with a small number of inputs. We've been able to validate these designs by generating test vectors for all possible input combinations and verifying the output visually in Modelsim. As we move towards 8, 16 and 32-bit systems, however, this no longer becomes viable. It would take both the simulator too long to run that number of test vectors and us too long to read over that many results. So we need to start getting smart with our testing. In the last lab session, we looked at the idea of random and constrained random testing as a way of limiting the number of test vectors applied in a simulation, whilst not missing out on any interesting results, and those are the models we're going to start moving towards from this session. However, to perform this type of testing, we need a way to generate random numbers in our test benches, and a way to automatically validate the results. Generating random numbers in Verilog is really quite simple. We've just got two different commands to use. The random function will generate a 32-bit signed integer, and the urandom function will generate a 32-bit unsigned one. So as you'll see shortly, we can generate these random values and apply them as test vectors. So this is a good start, but we don't always want a full 32-bit value. We'll usually need values within a range equal in width to our number of inputs, so we need a way to constrain the numbers generated. We can do this using the modulo function. The modulo function divides the generated random number by a given factor and returns the remainder. Therefore, if we use the desired maximum value plus 1 as our divisor, we'll limit the returned random numbers to a specific width. So as you can see in the examples here, we can easily generate 4 and 8-bit random integers. We can use these commands in our test benches to generate random test vectors. We generate random integers as wide as our inputs and assign them to the input registers. If we do this inside our for loops, we can generate a new set of test vectors every time the loop iterates. In this example, I've designed a test bench for an 8-bit adder. Everything looks the same as it has done in our previous test benches, but you can see that when we get to applying the stimulus, all I'm doing is generating random values and assigning them to the input registers to apply them to the device under test. Note that I've still got two separate test cases, one for when carry-in is 0 and one for when it's set to 1. This doesn't necessarily need to be the case. I could have concatenated all three inputs into one bus and applied a random 9-bit value to it to completely randomize the testing, but I may be wanting to keep some form of order in my test bench. We can view the results of this test in Modelsim. As you can see, every 100 nanoseconds we apply a random set of values to the inputs, and we can work out in our heads whether they're correct or not. We don't really want to be doing this for 200, 2000 or 20,000 different values though, so we could do with a more automated solution. By tapping into some more behavioural Verilog, we can start to work towards developing self-checking test benches. For these simplistic designs, we can quickly develop mathematical models of our devices under test and what they should be doing. We can apply our random test vectors to both the device under test and the model in parallel, and compare the outputs to check if our design works correctly. This, of course, depends on our mathematical model being correct, so we have to pay close attention to what we're actually implementing. In the example here, I've declared two integers, expected result and actual result. Then within the for loop, I set the expected result to equal the output of our mathematical model, which in this case is just the two inputs and the carry-in all added together, and the actual result to a concatenation of the carry and sum outputs, or rather the full numeric value generated by the adder. We then use a simple if statement to compare the two results, and if they don't match, a statement will display in the console, highlighting at which values any issues lie. Bear in mind that this will not fix the issues in my design for me. It's just a way of quickly highlighting which values cause problems, and then it's up to me as the designer to debug my circuit, check for any possible incorrect wirings or mislabeled gates or anything like that. Pay close attention to where I put the result assignments and the comparison. They all go after the delay statement. We'll cover this in greater detail when we talk about blocking and non-blocking statements in the second half of the semester, but it's definitely worth pointing out now. As we know, Verilog executes everything in parallel. It doesn't assign a random number to A, then a random number to B, then calculate the expected result from those and read the output. It does it all at once. Therefore, our result assignments and comparisons would execute at the exact same instant that the new values are assigned to the device under test. This means at this instant, the value of carryout and sum would be the values from the previous cycle and nothing would match. This is one of the key problems that we run into with behavioural Verilog. It's very easy to try and treat it like a procedural programming language when it simply isn't. And if you do this, you'll run into issues very quickly. So when we run this simulation, if everything's okay, nothing will be flagged up. However, if our design is incorrect, the output won't match its expected value and a warning will be triggered. This prompts us to return to the design and determine what's wrong. So with self-checking test benches, we no longer have to manually verify the results in Modelsim. We can just check to make sure nothing has gone wrong. This does, however, rely on us developing a reliable mathematical model in our test benches. Whilst this might be simple for an adder or multiplier, it would be a serious challenge for something like an HDMI driver or an FIR filter. And this is where the idea of the golden models that we discussed in the previous lab session come in. We can look at designing full software simulations for our devices under test so that we can compare them to the output of our digital designs. These rudimentary self-checking test benches allow us to increase the size and complexity of our designs without exponentially increasing the amount of time required to verify their functionality. Over the next few weeks, we're going to start working with more and more complex systems, so you need to start experimenting with developing these mathematical models as soon as possible.